In this section, we will define the so-called Laplace transform. The Laplace transform is an integral operator that will allow us to solve differential equations with algebra instead of calculus. So it works as follows. We take a differential equation with a variable t, and then we apply the Laplace transform. What happens is the differential equation becomes an algebraic equation with variable s. We can then use algebra to solve that algebraic equation, and we get an answer in terms of s. We then need an inverse transform that transforms the answer in terms of s into a solution in terms of t. So the Laplace transform is defined as follows. Let f of t be a function on the left closed interval 0 to infinity. The Laplace transform of f is the function capital F defined by the integral capital F of s equals the indefinite integral from 0 to infinity of e to the power negative st times f of t dt. The domain of capital F of s is all the values of s for which the integral exists. The Laplace transform of f is denoted by both capital F and curly L of f. So let's do an example with a very simple function to start out. So we're going to find the Laplace transform of the constant function f of t equals 1. So our function here is this function f of t is the constant function 1, and we want to find the Laplace transform of this function. So the Laplace transform of our function f of t is itself a function of s, and it's given by the Laplace transform of the constant function 1 right here. And by definition, this is equal to the indefinite integral from 0 to infinity of e to the power negative st times our function f, which is just the constant 1, dt. So now this of course simplifies to just e to the power negative st, and in order to calculate an indefinite integral, we will have to introduce a limit. So the indefinite integral is defined as the limit of n goes to infinity of the definite integral from 0 to n, and then the function is e to the power negative st dt. So we can then find the antiderivative of e to the power negative st and use the fundamental theorem of calculus. So we're going to still have the limit as n goes to infinity, and then the antiderivative of e to the power negative st will contain e to the power negative st. But this is not the correct antiderivative, because if we take the derivative of this, the chain rule tells us it's this function, and then we have to multiply by negative s. There's no negative s here. So to account for that, we're going to divide by negative 1 over s. And you can verify that if you take the derivative of this with the chain rule, you end up with this. So we have a correct antiderivative. So we then have to evaluate that function in n at 0. So remember that what I'm using here is the notation f of x b a is shorthand notation for f of b minus f of a. So when I have this, I have to plug in n and then subtract the value where I plug in 0. And all the while, I still have the limit as n goes to infinity. So if I plug in n in the first part, I get negative 1 over s, and then e to the power negative s times n. And then I'm subtracting from that the expression that I get when I plug in zeros. So that's minus 1 over s e to the power negative s times 0. Now, I can take the limit of all of this, but this is a constant in terms of n, so I only have to take the limit of the part that contains n. So now I need to figure out what this part is going to be. But let me first simplify that before we start worrying about the limit. So I have the limit as n goes to infinity. And I'm going to rewrite this a little bit. I can rewrite that as negative 1 over s, and then times 1 over e to the power s n. And then this becomes a plus, and that becomes a, this is 1, so that's plus 1 over s. So now what I need to figure out is what happens to this limit here. Now, if s is positive and n grows to infinity, then the exponent of e goes off to positive infinity. And what happens to the exponential function when the input goes to infinity is that this goes to infinity. So if we write that down here, so if s is greater than 0, then what happens to Sn? Then Sn goes to infinity when n goes to infinity. And that means that e to the power Sn goes to infinity. And that means that 1 over e to the power Sn goes to 0. So this right here is 0. 1 over s, negative 1 over s is a constant. So that whole limit evaluates to just 0 as long as s is greater than 0. So that is 0 plus 1 over s. And that's if s is greater than 0. And so if we summarize, we see that the Laplace transform of the constant function 1 is written differently. Capital F of s is 1 over s. And this holds as long as s is greater than 0. So that is our final answer for our Laplace transform.